today we shall discuss arithmetic functions. An arithmetic function is a function f from natural numbers to complex numbers. So for every n in n, there is f of n belonging to C. So fn can be an integer, rational number, real number, complex number. We can also think of an arithmetic function as a sequence, because we can consider f1, f2, f3, etc. These are the values of the function and these form a sequence. We have a few examples of arithmetic functions like this: fn equal to n, or we can take fk n equal to n raised to k for a fixed k bigger or equal 1. We can take, let us say, phi of n, which is the Euler's function. This is the number of positive integers less than or equal to n and relatively prime to n. Number of positive integers less than or equal to n and relatively prime to n. So this is an arithmetic function. We can think of other arithmetic functions also. One of the standard functions is the function dn, or in some books it is denoted by tau of n. This is the number of divisors of n function. So d of n equal to the number of positive divisors of n. For example, if I take the number 20, then 20 has divisors 1, 2, 4, 5, 10 and 20. So d of 20 equal to 6. We can also take sum of these divisors, and that function is denoted by sigma of n. Sigma of n equal to the sum of divisors of n. For example, here what is sigma of 20? That is 1 plus 2 plus 4 plus 5 plus 10 plus 20, and that's equal to 42. Sigma of 20 is 42. We can think of sigma k of n, which is the sum of kth powers of divisors of n, sigma kn. So sigma 2 of n, sigma 2 of 20 will be 1 square plus 2 square plus 4 square plus 5 square plus 10 square plus 20 square, like that. Some other standard functions are Pn, the number of partitions of n. Like if you take a number, let us say 5, then 5 you can write as 5 itself, you can write as 4 plus 1, you can write as 3 plus 2, you can write as 3 plus 1 plus 1. You can write also as 2 plus 2 plus 1. Then 2 plus 1 plus 1 plus 1. And also 1 plus 1 plus 1 plus 1 plus 1. So you can write partitions of 5 in these 7 ways. And so we say P of 5 equal to 7. This is an interesting function and it appears in many contexts in combinatorics. And Ramanujan gave a formula for P of n which is well known. Hardy and Ramanujan gave a formula. Some other functions are like this. Omega of n equal to the number of primes, means distinct primes, dividing n. And you can define capital omega n equal to the number of primes dividing n counted with multiplicity. Multiplicity. For example, if I take omega of 20, small omega of 20, here the primes dividing 20 are 2 and 5, so this is 2. If I take capital omega of 20, then note that 20 is equal to 2 square into 5. So 2 is coming 2 times and 5 is coming once. So capital omega of 20 is equal to 3. We can interpret capital omega in a different way also. Capital omega of n, you can also think of the number of distinct prime powers dividing n. Like 2 divides 20, 2 square divides 20 and 5 divides 20. So there are 3 prime powers dividing the number 20. So capital omega of 20, you can say it's equal to 3. Obviously capital omega of 1, that is 0, capital omega, small omega 1 and capital omega 1 both are 0. No prime or prime power divides 1. We can also construct new arithmetic functions from old ones, and this can be done like this. If Fn is an arithmetic function define capital Fn equal to summation fd d divides n. Summation fd d divides n. This is of course an arithmetic function, and as an example we can think of, suppose original function is phi, the Euler's function. From this you can get a new function. What is that? Let us find out. So small fn equal to, say, phi of n, Euler's function. What is capital Fn? This is summation phi of d, d divides n. Now take an example like n equal to 24 and let us calculate capital F of 24. So the divisors of 24 are like this. They are 1, 2, 3, 4, 1, 2, 3, 4, 6, 8, 12 and 24. Now let us find out phi of these things. So this is D, let us say phi of D. So the Euler's function is phi of 1 is 1, phi of 2 is also 1, phi of 3 is 2, phi of 4 is 2, phi of 6 that is again 2, phi of 8 is 4, this is 4, and phi of 24 is 8. And if you take summation phi of D, D divides 24, this comes out to be exactly 24. Anyway, so for any number n, we can find out summation phi D, D divides n. It's a result, interesting result, that this summation phi D, D divides n always comes out to be equal to n, and that we will see later on. So summation phi of D, D divides n is equal to n. That is an interesting result that we shall see. So these are some examples of arithmetic functions. You can define values which are not integers also. Like a standard function is lambda of n. It is defined like this. If n is a power of a prime, then you define it as log of p. If n is power of a prime, p raised to k, p prime k bigger or equal 1. And this is defined to be 0 otherwise. So we have an interesting function like this. We will now see how we calculate values of some of these functions. For example, the function d of n, number of divisors of n. So given a number like n equal to 100, how many divisors does this number have? We do it like this. The prime factorization of this number is important. So write n equal to p1 raised to a1 etc. pr raised to ar. This is the canonical factorization of the number n. Canonical factorization. That means pi are distinct primes and ai are bigger or equal 1. Pi distinct primes and ai are bigger or equal 1. Now what are the divisors? So any divisor of n is, so if you take this number n, a divisor may or may not contain these primes p1, p2, pr. If it has some prime, let us say p1, then the power of p1 which is appearing in that divisor can be at most a1, it cannot be more than that. Also the primes other than p1, p2, pr, they cannot occur in any divisor. So any divisor of n is of the form P1 raised to B1, P2 raised to B2, etc. PR raised to BR, where these BI are less than equal to AI. BI less than equal to AI, but they can be 0, that is some prime may not appear in that factorization of the divisor. So we will say 0 less than equal to BI less than equal to AI. Now from the fundamental theorem of arithmetic, we know that these BI are uniquely determined for a divisor. So how many possibilities are there for these BI for a given I? BI can be any number from 0 to AI. So 0, 1, 2, 3 up to AI. So the possibilities for BI are AI plus 1. Each BI has AI plus 1 possibilities. Okay, 0 less than equal, so 1 less than equal to I less than equal to R. For each I, BI has AI plus 1 possibilities. And these different possibilities give rise to different divisors of the number n. And therefore, what is the number of divisors of n is, we have to use the multiplication principle, that B1 has A1 plus 1 possibilities, B2 has A2 plus 1 possibilities, BR has AR plus 1 possibilities. So the number of divisors of n is, which we write as D of n, that is A1 plus 1, A2 plus 1, etc. AR plus 1. This is the formula for number of divisors of n. For example, if you take n equal to 100, you can write this as 2 raised to 2 multiplied by 5 raised to 2, and then these are the values of AI. A1 equal to 2 and A2 equal to 2. Therefore, D of 100, number of divisors of 100 is equal to 2 plus 1 into 2 plus 1, that's equal to 9. So 100 has 9 divisors. We can also find out the value of the function sigma n, but before that we will define a multiplicative function. So what's a multiplicative arithmetic function? An arithmetic function Fn is said to be multiplicative if it is not identically 0 and the main property is that f of mn equal to fm into fn whenever GCD mn is equal to 1. Such a function is called a multiplicative function. This condition is to avoid the trivial example that fn equal to 0 for all n. And this also will tell you that f of 1 is always 1 whenever the function is a multiplicative arithmetic function. So note, if fn is multiplicative. This is a multiplicative arithmetic function. Then f of 1 equal to 1. You will see that d of 1 is 1, number of divisors, sigma of 1 is 1, and many other functions will have this property. These are actually multiplicative, and that's why this is happening. Let us see why this happens. So first of all, since f is not identically 0, what happens? There is some n such that fn is not equal to 0. There is n bigger equal 1 such that f of n is not equal to 0. Okay, now we can consider n and 1, they are coprime. GCD of n and 1 is 1. So we can say f of n, we can write as f of n into 1, which is f of n into f of 1. But now fn is not equal to 0, so we can cancel fn and get f1 equal to 1. Since f of n not equal to 0, we get, by cancelling fn, f1 equal to 1. This happens for any multiplicative function. And a very interesting thing is that if fn is a multiplicative function, then the derived function capital Fn is also multiplicative. So if Fn is a multiplicative arithmetic function, then so is capital Fn equal to summation Fd d divides n. So is summation Fd d divides n. This is a very useful property. The proof also is simple. So we consider n and m as coprime integers. Let nm equal to 1. Then capital F of mn this we have to show it is equal to f of m into f of n, where n and m are coprime. So summation f of d divides mn. Summation fd d divides mn. So d varies over divisors of mn. And what can I say about divisors of mn? Mn is our coprime. So primes in m and primes in n, they are different primes. Any divisor of mn, it may have some primes coming from m and some primes coming from n, and their appropriate powers. So let us write d1 equal to GCD of d with m and d2 equal to GCD of d with n. Then d is d1 d2, where d1 is a divisor of m and d2 being a divisor of n. And such d1 d2 are uniquely determined, that when you write D as a product of D1 and D2 with D1 dividing M and D2 dividing N, such D1 D2 are uniquely determined. D can be written uniquely as D1 D2 in this way. And given a divisor D1 of M and a divisor D2 of N, you get a divisor of Mn. So given D1 dividing M, D2 dividing N, clearly D1 D2 divides Mn. This is a divisor of Mn. So what we do is we write every divisor of Mn uniquely as D1 into D2. So we can say that f of Mn equal to summation f of, write D as D1 D2, where D1 divides M, D2 divides N. This is possible because M and N are co-prime. Now, especially uniqueness. Now you write f d1 d2 as f d1 into f d2. So summation d1 divides M, d2 divides N, f of d1 into f of d2. That is because the function f is multiplicative and d1 and d2 are also co-prime, because M and N are co-prime. Therefore the divisors of M and N, they are also co-prime, and so we can write f d1 d2 as f d1 into f d2. So since f is multiplicative and d1 d2 equal to 1. Alright, so this is a double summation, that summation over d1 as well as d2, f d1 into f d2, and this we can write as equal to f d1 summation d1 divides M into f d2 summation d2 divides N, and this is nothing but capital F of M into capital F of N. Here M and N are co-prime, f of Mn equal to Fm into Fn. That shows that capital F is also multiplicative. Therefore capital F is also multiplicative. Okay. The second property we have proved. The first property is actually trivial. See, what is capital F of 1? It is summation fd, d divides 1. So this is f1 only, and that is 1. So capital F is a non-zero function. It's not identically 0. So that is the first property, and this is the main property, that f is multiplicative. And this is very useful in finding formulae for some arithmetic functions which are multiplicative. So start with a multiplicative function, get a new function, and it will also be multiplicative. So here actually the function sigma of n was summation d divides n, and this function actually that we had considered was like this. This is summation f of d divides n, and this fd was d. So original function is somewhat different. F of n equal to n, that is the function that we are considering here, and this is a multiplicative function. Multiplicative function, and this is multiplicative, therefore the summation of fdd divides n is multiplicative. So sigma of n is multiplicative, and we can find out sigma like this. So sigma n is multiplicative. Okay, so write n equal to p1 raised to a1 etc. pr raised to ar. This is the canonical factorization of n. Now note that when a function is multiplicative, f of mn equal to fm into fn whenever m and n are co-prime. This we can extend. If n1, n2, nr, they are co-prime in pairs, then f of n1, n2, nr will be f of n1 into f of n2 into f of nr. This happens when the function f is multiplicative. So the values of the function are known if you know the values of the function at prime powers. That is what we shall be using here. Therefore, sigma of n is equal to sigma of p1 raised to a1 etc. sigma of pr raised to ar, because these are mutually co-prime. Various prime powers corresponding to different primes are co-prime in pairs, and we can use the multiplicative property. Now what is sigma of pi raised to ai? So take any prime p and take a power. So now for a prime p and a bigger equal 1, sigma of p raised to a equal to, so sum of divisors of p raised to a. So it is 1 plus p square etc. plus p raised to a. And here this is a geometric series with first term 1, common ratio is p, and the number of terms in the geometric series is a plus 1. So this is equal to p raised to a plus 1 minus 1 upon p minus 1. And now you can use this to get sigma of n. Therefore sigma of n equal to summation. So this is product of, we can say, sigma of pi raised to ai I equal to 1 to r, and that is product of pi raised to ai plus 1 minus 1 upon pi minus 1. Okay, in this fashion we can also get sigma kn, which is sum of kth powers of divisors of n. So consider sigma kn equal to sum of kth powers of divisors of n, and this is, we can say, summation d raised to k, where d divides n, and this is to be considered as summation d divides n f of d, where now this fd is same as d raised to k. So we can say where f of n is n raised to k. So here fd is d raised to k, that means f of n will be n raised to k. This is the function and this is a multiplicative function. Okay, now since fn is multiplicative, the function sigma kn obtained from fn is also multiplicative, and therefore the values of sigma kn can be obtained from the values of the function at prime powers. So if n equal to product pi raised to ai, I equal to 1 to r, this is canonical. Canonical means pi are distinct primes and ai are bigger equal 1. Then sigma k of n equal to product sigma k pi raised to ai, I equal to 1 to r. Sigma kn can be obtained from sigma k at prime powers. What is sigma k pi raised to ai? So take any prime p for p prime and a bigger equal 1, sigma k of p raised to a. What is that? So you should take the divisors of p raised to a and take their kth powers. So these are, so 1 plus p raised to k plus p raised to 2k plus etc. plus p raised to a times k. And this is again a geometric series whose first term is 1 and common ratio is p raised to k. And the number of terms is a plus 1. So geometric series with first term 1, common ratio p raised to k, and number of terms equal to a plus 1, and therefore sigma k p raised to a will be equal to p raised to k raised to a plus 1 minus 1 upon p raised to k minus 1. And then from this we can get sigma kn. Therefore sigma kn equal to product sigma k pi raised to ai, which is product pi raised to k raised to a plus 1 minus 1 upon pi raised to k minus 1, I equal to 1 to r. So this is how you get sigma kn. Using that, it comes from a multiplicative function and therefore it is also multiplicative. Let us now prove the interesting result about the Euler's phi function. So theorem. If phi denotes Euler's function, then summation phi d d divides n equal to n. Summation phi d divides n equal to n. We had verified this when n was 24. We can now prove it for any n. To prove this, consider the function phi n, which is a multiplicative function. So phi n is multiplicative. Phi n is multiplicative. Therefore, the function which is obtained from phi of n in this fashion, summation phi d divides n, that is also multiplicative. Therefore, f of n equal to summation phi d divides n is also multiplicative. Once the function is multiplicative, you can obtain it from its values at prime powers. So what is f of p raised to a for any prime p and any a positive integer bigger or equal 1? So this is summation phi of b d divides p raised to a. Here p is prime, a bigger or equal 1, that is assumed. And now write down the values of phi d for various divisors. So any divisor d of p raised to a will be p raised to b, where b is less than or equal to a and it's a non-negative integer. So it is like this. This is phi of 1 plus phi of p plus etc. plus phi of p raised to a. 1 p square etc. p raised to a. These are various divisors of p raised to a, and take phi of these and add. What is this? So phi of 1 is 1, phi of p is p minus 1, phi of p square is p square minus p, and so on. And finally, phi of p raised to a is p raised to a minus p raised to a minus 1. And when you simplify this, so 1 gets cancelled, p gets cancelled, and so on. Ultimately, only this term remains, so it is p raised to a. So, capital F of p raised to a comes out to be equal to p raised to a itself. And therefore, if you write down this n as product pi raised to ai, I equal to 1 to r, canonical factorization, then f of n equal to product of f of pi raised to ai, I equal to 1 to r, because capital F is multiplicative. Okay, capital F is obtained from pi by the standard procedure, and it is also a multiplicative function because pi is multiplicative. And all these f of pi raised to ai, they are just pi raised to ai. So it is product of pi raised to ai, I equal to 1 to r. And therefore it is just the original number n. So capital F is the identity function, fn equal to n. And this shows that thus summation phi d divides n comes out to be equal to n. In fact, this is the reason why this phi is called totient function. Totient refers to parts, so the number n you can partition in this way using the Euler's phi function corresponding to the divisors of n. For every divisor d, you find out phi of d, and n can be partitioned. N is sum of all these phi d. That's why this phi is called totient function. So because of this, identity phi n is called totient function. The word totient refers to parts. Now, what we have seen for the function capital F obtained from small f in a particular manner. That is, if small f is multiplicative, then capital F is also multiplicative. The same is true for functions obtained from two different functions in a specific manner, which is called as Dirichlet multiplication of two functions. So let us study that. Define for two arithmetic functions f and g, the Dirichlet multiplication f star g as follows. So f star g of n equal to summation f of d g of n by d, d varying over divisors of n. F star g of n is summation fd g n by d, d dividing n. You can write this in different ways also, like you can interchange d and n by d. So you can say summation f n by d g d, where d divides n. Or you can understand that the product of these two is n. So you can write it as f d1 into g d2, where d1 into d2 is equal to n. So these are different ways of writing the same thing. So observe that. F star g of n is equal to summation f of n by d g of d, d divides n. Or you can also write it as summation f of d1 g of d2, where d1 d2 is equal to n. Product of d1 and d2 is n. So this is a way of getting new arithmetic function from two arithmetic functions f and g. And the previous thing that we considered can be understood as a particular case of this, that is getting capital F from small f. Let us see how that is a particular case of this. So define u of n equal to 1 for all n. Define u of n equal to 1 for all n. This is an arithmetic function. And what is f star u of n? This is summation d divides n f of d u of n by d. Okay. Now what is u n by d? D is an integer dividing n by d is an integer. U of n by d, you see the definition of un is equal to 1 for all n. So u of n by d is 1. And therefore, this is just summation fd d divides n. So this is 1. So this is summation fd d divides n. And you see that this was the function capital F obtained from small f. In fact, as we have seen that capital F is multiplicative when small f is multiplicative. In a similar manner, we can show that if f and g are both multiplicative functions, so is f star g. That is also true. So let us see that, and the proof is actually similar. So theorem, if f and g are multiplicative, so is f star g. So is f star g. To say this, what is f star g of mn, where m and n are coprime, mn equal to 1. We are assuming that mn equal to 1. Assume f and g are multiplicative. Now this is summation d divides mn f of d g of mn by d. mn by d. Okay. Now, as d varies over divisors of mn, you can write any such divisor as d1 into d2, where d1 divides m and d2 divides n. And these d1 and d2 are determined uniquely and they vary over respectively divisors of m and divisors of n. Any divisor d of mn can be uniquely written as d equal to d1 d2, where d1 divides m, d2 divides n. And conversely, if d1 divides m, d2 divides n, then d equal to d1 d2 is a divisor of mn. Also, for d1 dividing m, d2 dividing n, d1 d2 divides mn. As d varies over divisors of Mn d1 d2 vary over divisors of M and N respectively. Divisors of M and N respectively. So d1 varies over divisors of M and d2 varies over divisors of N. Therefore, this summation d divides Mn fd into g Mn by d. So this d we can write as d1 into d2. And so f star g of Mn will be like this. So here f star g of Mn we can write as summation d1 divides M, d2 divides N, f of d1 d2 g Mn by d1 d2, which can be written as, because f is multiplicative and g is multiplicative, summation d1 divides M, d2 divides N, f of d1, f of d2. Now this we can write as m1 by m by d1 and n by d2. These two are also co-prime. So g of m by d1 into g of n by d2, because fg multiplicative and d1 d2 equal to 1, as also m by d1 n by d2 equal to 1. And therefore this can further be written as summation f d1 g m by d1. This we can take in one bracket. Here d1 divides m. In the second bracket we can take d2 divides n, f of d2 g of n by d2. And this is nothing but f star g of m. And this second bracket is nothing but f star g of n. So f star g of mn equal to f star g of m into f star g of n whenever m and n are co-prime. And this shows that f star g is multiplicative when f g r. That proves the theorem. We will see how this result can be applied to usual arithmetic functions. صلاة أظن اقتص